What's going on, everyone? I hope you guys have a great day so far. It's Ben, and today we're going to be covering U substitution. I'm going to be going over 3 examples. The first one being pretty easy, second one being medium difficulty, and the third one being challenging, so you guys can learn how to use U sub and when to use U sub. Let's get right into it. So, getting right into what U sub is all about. U sub is to help us simplify and work with integrals that we can't just take the antiderivative of right away. It helps us simplify integrals so we can then recognize, oh, we need to use this antiderivative formula. And before we get into some examples, I'm going to talk about when do we use it and why do we use it, and what to look out for, right? So what I have written here is some choices of U sub. Most of the time, the option that you should be choosing for your U sub will usually be inside of a square root, or will be inside of an exponent, or will be inside of some parentheses. There's plenty of other options that could be, but these are the main 3 cases that you want to look out for. And another thing that's really important that I want to make clear is that U sub, that choice of U sub, when you take the derivative, should be somewhere else in the integral. Let me repeat that. The choice of U should have its derivative somewhere else in the integral, so then they can cancel out and making the integral look a lot more simple and we can work with it. If you don't understand exactly what I'm saying, I'll showcase some examples using what I'm talking about. But what I have written here is kind of what I was trying to make clear. So if we have a function or an integral, right? Several parts of it, but we have a somewhere with the square root and we have a function within the square root. If we make that function our U sub, so if we make our U equal to this f of x, and we take the derivative, right, which is what we do with U sub, boom, look, do we have an f prime somewhere? Yeah, we do, right here. We can go ahead and just substitute that in, cancel them out, however you like to say it. I'll be showing you guys exactly what I mean here. And for the next case, it's very similar to what I just said. If we have a function if we have an integral, right, with a function in the exponent, most of the time it's with ease. You want to look, if I take this and make this as my U sub, is its derivative somewhere else? Keep that in mind. Same thing, last but not least, same thing with the cosines or any trig functions. You want to look, most of the time, the U sub would be inside of the trig function, and its derivative will be somewhere else in the integral. So hopefully when you make that your U, you cancel them out nicely. Let me show you guys exactly what I mean with this first example. So for the first example, it's going to be the integral of x squared times the square root of x cubed plus 5 dx. So right off the bat, there's not much what we can do with this integral, right? We can't just take the antiderivative. It's 2 completely different functions being multiplied by each other. This is a perfect example of U substitution, right? We have a square root, so let's go ahead and look inside of the square root and make that our U and see if that works, right? So let's go ahead and set this inside equal to U. So we're at U is equal to x cubed plus 5. And next step, what we do is take the derivative of both sides. And when we do the derivative with U sub, it looks a little bit different if you're new to this, right? But when we take the derivative of both sides, on the left side, we get du equals, then we take the derivative of the right side normally with respect to x. So we're going to go ahead and apply the power rule, 3x squared, and then the derivative of a constant is a 0. So at the very end, we're going to go ahead and just slap on this dx. That's what we do every time. We make it the left side just a du, the right side will just be dx, or the derivative times dx. And so now, this is perfect. Look, this looks very similar. We have a 3x squared right there, and here we have an x squared. It looks almost the same, right? So let's go ahead and do the next step and continue forward with this process. So what I like to do, I like to solve for dx now, because we need to get this integral in terms of u's only, get rid of all the x's, right? So we need to change this dx into something with du times like a function. So we have dx right here, and we have dx right here. We need to go ahead and solve for dx. So just simple algebra, getting this dx by itself, meaning we divide both sides by 3x squared. This will turn to 1, right? So now we have du over 3x squared equals to dx. Perfect. So now we can go ahead and rewrite this integral with our new substitutions. So we know that inside the integral, and inside the square root is going to go u. So what we have is x squared times the square root of u. Remember, we're not going to attach dx. Our dx is actually equal to du over 3x squared. So that's what we're going to plug in instead of dx. So we have du over 3x squared. And perfect, right? All these things are being multiplied by each other, so we can rearrange them however we'd like. And we'll notice that here, we can imagine this as being x squared over 1. So we can multiply everything together, and we'll end up seeing that we'll have an x squared on the top in the numerator and an x squared in the denominator. Remember, if we have one thing divided by the same thing, this turns into 1. So we have this x squared, and we have another x squared right there. Turns into 1. We can just go ahead and remove it from the integral completely. So now let's go ahead and simplify our integral after canceling some stuff out. So now we have the square root of u times du over 3. Look, it's a lot more simpler now, right? We can go ahead and bring out that 1/3, right? That's a 1/3. In my last video, I explained how we can just pull out constants like that. So now we're just left with the square root of u times du. Very simple. This is a table integral. We're just going to go ahead and apply the reverse power rule from here on out. So we're going to continue to bring the 1/3 with us. Times, remember, u square root is equal to just u to the 1/2, right? So when we're going to add 1 using the reverse power rule, divide by the new power, right? So now we have u to the 3/2 over 3 over 2 plus c. Right? We can go ahead and simplify these constants in the front, right? Remembering that dividing by a number is the same thing as multiplying by the reciprocal. So we're going to go ahead and do that now. So we have this 1/3. We're going to multiply it by the reciprocal of, so 3/2, the reciprocal of that is 2 over 3. And we still have the u to the 3/2 plus c. We're almost done now. So now let's just go ahead and multiply those together. So we have 2 over 9 u to the 3/2 plus c. We're basically done, right? We have the integral. We found the antiderivative. We have attached our plus c. The last step is just to replace our answer in terms of x's. We don't want to end off with u. That's not correct. We want to end up with an answer with x's in it. So let's go look back at what our u sub was. Our u sub was x cubed plus 5. So we're just going to go ahead and plug that into where our u was. So we have 2 over 9. We're just going to go ahead and do a parenthesis. X cubed plus 5 to the 3/2 plus c. Boom. Final answer, done. Very simple, very satisfying. This is a great example of u sub and how it works, why it works. This is probably the most simple example that you can ever, not most ever simple example, most simplest example, but this is a great example to learn exactly why do we use it and when do we use it. So with that being said, let's get on to the next example. It's going to be a bit more challenging, but I think this is great for you guys to learn. Okay, on to the next example. Let's go ahead and approach this with what we know. So right off the bat, we're not really seeing any square roots. We're not really seeing any parentheses. We're seeing some trig functions, right? But I don't think we would want to make our u sub what's inside the trig functions, right? It's just x. That won't really help us. It's not going to cancel anything out, right? The derivative of x is not really anywhere in our integral. That's very important. So let's go ahead and approach this thinking outside the box. So remember what I said, the choice of u needs to look like something else that we have in the integral already, right? Thinking the derivative of secant, if we chose u to be secant, the derivative of that is secant tangent. But don't write this down yet. We have secant tangent. Yes, we do have a tangent in there, but it's a 1 plus tangent. That won't really cancel out. That's one whole term. The 1 plus tangent is one whole term. That doesn't really help us. We can't really cancel that out. It's not the same thing as secant tangent, right? So maybe, yes, I think you could go forward with this u sub. It might take a little bit more skill, a little bit more manipulating. But if we just choose something else, if we choose something else for our u sub that I see right here, it would be way quicker and way easier. So let's go ahead and choose tangent or 1 plus tangent as our u. It's always better to just, if you see a constant plus tangent or whatever trig, whatever you're doing, it's always good to choose that whole thing as your u because that constant will just go away, right? So let's go 1 plus tangent x, derivative of both sides. 1 just turns to 0. Tangent turns into, the derivative of tangent is secant squared. And if you guys don't know how to get that, how I got that, I recommend keeping a table of derivatives by your side when practicing these, because it's something if over time you just memorize it. You could derive the derivative of tangent; it just takes longer. If you just remember that it's secant squared, perfect. So now look, we have a secant squared there. So solving for dx, right? That's our next step, solving for dx. So we can plug that in. We just divide both sides by secant squared. So that will end us off with du over secant squared x equals dx. Beautiful, right? We have our u, we have our dx. So let's go ahead and rewrite our integral in terms of u. So our secant squared is going to still be on the top, right? That wasn't our u this time. Then this whole bottom part is going to be our u, which is nice, cleans it up a lot, and times our dx. Remember, our dx was du over secant squared x. So let's go write du over secant squared x. And look, perfect, right? We have a secant squared over a secant squared. That just turns to 1. So we can go ahead and cancel that out completely. And then rewriting this integral, right? We just have 1 over u times du. Look, super easy. We know what the antiderivative of 1 over u is. If you don't remember, it's okay. Keep practicing. 1 over u is just going to be natural log of u, or absolute value of u. So we're going to go ahead and just write that down. Natural log, absolute value of u, plus c. And that's it. I know the integral looked a lot scary at the beginning, but the simple u sub made it really quick and made it really easy to integrate. So now, remember, last step, plugging in our u's. What was our u? It was 1 plus tangent. So let's go ahead and just rewrite this as natural log, absolute value, of 1 plus tangent x plus c. And boom, that's our final answer. And remember, quick side note, if you always want to just double check your work, if you're like on a test or something, you can just take the derivative of your final answer. So we can just do that real quick. I'll just do it for you guys. Derivative of natural log is just 1 over whatever is on the inside times the derivative of the inside. 1 plus tangent, derivative of that is secant squared. And that's exactly what we have. So boom, our answer is correct. Wonderful. Another great example. A little more trickier because of trig, but nothing that you can't understand and can't get through with as time goes on and you have way more practice. So let's get on to the third and last example. It's going to be a little more trickier, but it should be fun. Okay, on to the next integral. We have the integral of 1 over the square root of x times 1 plus x. And from what we're seeing right away is that, yes, we do have a square root. Yes, we do have a function within some parentheses. But remember that u sub needs to have its derivative somewhere in the integral. And inside the square root, we just have x. Derivative of x, just 1. Yes, we do have a 1, but it's 1 plus x. It's not going to help us. We take the derivative, make the u sub of 1 plus x. That's the same thing. It's just still going to be 1. That doesn't help us either. But instead of just doing x, I'm going to tell you guys right now, we're going to make the u sub the square root of x. And this is a more trickier problem. I don't expect you guys to understand this right away. This will take some time to understand. But we're going to have to do a little bit of manipulation. But you can expect to see a lot of these type of problems in your homework, and especially in calculus too. So let's get right into it. So now that we made a choice of u sub as the square root of x, next step, to take the derivative of both sides. Remember, derivative, it's a table integral, table derivative. It's just 1 over 2 square root x dx, right? Remember, next step, get the dx by itself, meaning multiplying both sides by 2 square root x. So then we get 2 square root x du equals dx. Not bad, but remember what our u sub was. Our u was square root x. What do we have here? Square root x. So we can go ahead and write 2 times u du is equal to dx. Boom. Wonderful. Let's go ahead and rewrite our integral in terms of u now. So we have the integral of 1 over u times 1 plus x And then remember what our dx was? It was 2u du. And look, this is nice, right? This u and this u cancel. Wonderful. Let's go ahead and rewrite the integral now. We can bring that 2 completely outside of the integral. Remember that? Constant multiple rule. So now we have 1 over 1 plus x du, right? Like, what the heck? What's going on? We still have x's and we have a du. We can't integrate with x's with respect to du. That doesn't make any sense. So we need to get that 1 plus x into terms of u. How can we do that? Well, let's go take one step back and let's go look over here of what we chose for our u. Our u was equal to square root of x, but we can do a little bit more tricks. Let's go ahead and bring this down here. We have u equals square root of x. Sorry. This is just an equation. We can do anything we want to it. We just have to just do what we do to one side, we must do to the other. So, squaring both sides, we get u squared equal to x. Look, that's almost what we have here. We have an x plus 1. So what if we just add 1 to both sides? Look, now we know what our u sub is. What 1 plus x is equal to, right? We have 1 plus x here, we have 1 plus x here. That means we can substitute this into here. I know it's a little tricky, it looks a little weird. Looks like, how can we do that? I mean, they're the same equations. We're just rearranging them, right? It's still an equivalent statement, still a true statement. We're keeping equivalent by doing things to both sides. So now we have 1 over 1 plus u squared du. And boom, we're done. This is in the form of a table integral. You can go ahead, if you have a table of integrals, you can see the form of 1 over a squared plus u squared. A being a constant, our constant is 1, and square, we can just go ahead and just write 1 squared, same thing, 1 squared is just 1. We have this form, and whenever you have this form, the antiderivative is just, it's going to be 1 over a times tangent of u over a plus c. That's the formula for this type of integral. So with our case, let's go ahead and take the antiderivative now. So we have this 2 on the outside, don't forget that, times 1 over a, right? When our a in this case is just 1. 1 over 1 is just 1, right? So we don't have to write that. We're just going to write 2 times tangent. Sorry, it's inverse tangent. So sorry. Inverse tangent. And then we're going to write our u, not u squared. The formula is u over a. So it's going to be u, not u squared, just u, over 1. Or u divided by 1 is just u, plus c. And boom. That's basically it. We just have the last step of is making our integral in terms of x's again. So let's go ahead and do that. So now we can keep this the same. We have the 2 times inverse tangent. And let's go back to look at what our u was. Our u was square root of x. So let's go ahead and just write square root of x plus c. And that, my friends, is the answer. Pretty easy. Now that I know, at first it was like, what the heck are we doing, right? But it wasn't that many steps. The only tricky part that we did was just rearranging our u. We can do that. We can do that all the time. Whenever you see something that's not canceling out after doing a u sub, either you did the wrong u sub, or you can try rearranging some stuff, going back to your u sub, maybe square rooting both sides, or adding 1, or dividing one. I mean, by dividing by something, subtracting by something. Test some things out. It's very possible that you can solve the integral just by doing a bit more manipulation. And this is a prime example of when you can do that. And let's see. Let's go over one more example. One more pretty tricky example so you guys can fully understand. Next example, the last example, we have the integral of ln x squared, the whole thing is squared, over x. So, right off the bat, let's take a look. What should we use for our u? If we just choose x, that's not really going to help us. It's just going to change all the x's to u's. So, let's go ahead and try making our u natural log of x, right? It's really the only other choice we have here. It's inside of a parentheses. Just go ahead and try it out. So we're going to go ahead and do u equals the natural log of x right? Next step, derivative of both sides. We get du equals derivative of natural log is 1 over x, or 1 over whatever variable you have, dx, right? So that's perfect. Now remember what we do. We solve for dx. So we're going to multiply x to both sides, right? These cancel out, turn to 1. We have x times du equals dx. Wonderful. Let's go ahead and replace all of our x's with u's. So now we have u squared over x, remember x is still there, times our dx. What's our dx? X times du. And look, what can we do here? Give you guys a second to try to answer yourself. Like we've been doing every other problem. Cancel out the x's, right? So now we have just the integral of u squared times du. Boom. Pretty simple. We can just take the antiderivative of this right away. Just reverse power rule. We have the form of x to some n, right? So we can just go ahead and just add 1 to the power and divide by that new power plus c, giving us 1/3 u to the third. Done, right? That integral looked pretty tricky at first, but look, very simple. Making the right u sub makes the integral super easy and super nice to look at, right? So let's go ahead now. Last step, replacing our u's with our original u substitution. So now we have just 1/3 times the natural log of x cubed plus c, and that's it. Very, very easy. I just keep trying problems, u sub problems from textbooks, from YouTube. Just keep on trying them. I promise you guys, if you're having trouble, just keep doing them. Keep trying challenging problems. That's what I can't stress the most. Doing easy problems won't push you outside of your comfort zone, won't make you really think, won't make you do extra research. And doing these hard problems will really make you think outside the box. And that's really important in math. It really make you think, right? So, yeah, that's all my examples for today. I hope you guys really enjoyed the video. Just make sure to stay tuned, subscribe, leave a comment, follow me on my social medias. And yeah, hope you guys have a great rest of your day.